everyone, welcome back to the STEM Research Society. My name's Abby.
I'm Zina.
And I'm Michelle.
We'll be diving into some fascinating new research findings covering a wide range of topics, from treating bipolar disorder to the Riemann hypothesis to fog saunas. Stay tuned as we explore the latest discoveries from the week of July 8th to July 14th. Handing the mic over to Zina.
Thanks, Abby. Today, we will be diving into a groundbreaking study published in the Nature journal that reveals new insights into Alzheimer's disease. Scientists have used advanced imaging techniques to peer deep into the molecular world within an Alzheimer's affected brain. Alzheimer's disease, the leading cause of dementia worldwide, remains a daunting challenge in medical research. Recently, researchers at the University of Leeds, in collaboration with Amsterdam UMC, Zeiss Microscopy, and the University of Cambridge, have made significant strides. Using cryo-electron tomography and fluorescent microscopy, they've unlocked three-dimensional maps revealing the intricate molecular structures inside Alzheimer's brains. They zoomed in on two key proteins, beta amyloid and tau beta amyloid. These form microscopic plaques, while tau aggregates into abnormal filaments within brain cells. These proteins are notorious for disrupting cellular communication and causing the hallmark symptoms of Alzheimer's, such as memory loss and confusion. Dr. Rien Frank, the lead author and researcher, explained that this study marks a pivotal moment. It not only provides crucial insights into how these proteins behave in Alzheimer's brains, but also sets a precedent for studying proteins directly within their native environment, human tissues ravaged by disease. So, what are the implications for future research and treatments? The hope is that by unraveling the complex interplay of proteins in diseases like Alzheimer's, researchers can identify new targets for therapies and diagnostics. Understanding how these proteins interact and influence each other could pave the way for next-generation treatments that target the root cause of disease. This study overall underscores the importance of structural biology in unraveling the mysteries of neurodegenerative diseases. As we continue to advance our understanding, we move closer to effective treatments and, ultimately, a cure for Alzheimer's. Continuing on, we're delving into a fascinating study published in JAMA Psychiatry exploring a novel approach to treating bipolar disorder. At the University of Pennsylvania, research led by Dr. Yvette Aishelin investigated a cutting-edge therapy known as intermittent theta burst stimulation, or AITBS. This technique aims to tackle treatment-resistant depression in individuals with bipolar disorder, offering hope where conventional methods fall short. So let's break it down. AITBS involves using electromagnetic fields to induce changes in specific areas of the brain, aiming to enhance neuroplasticity and alleviate depressive symptoms. So, in this study, which was double-blind and sham-controlled, 24 patients with treatment-resistant bipolar disorder were enrolled. They underwent 5 days of treatment, which each day comprising of 10 sessions of either active AITBS or a sham procedure. The researchers used the Montgomery-Åsberg Depression Rating Scale, also known as the MADRS, to measure the severity of depression before and immediately after and 4 weeks post-treatment. So, what did they find? Well, patients who received active AITBS showed a remarkable improvement in their MADRS scores. For instance, their average score dropped significantly from 30.4 to 10.5 right after treatment. In contrast, those who received the sham treatment saw less change, with their scores decreasing from 28.0 to 25.3. Wow, that's super impressive. Secondary measures like the Hamilton Depression Rating Scale and the Beck Depression Inventory were also used to assess outcomes throughout the study. Dr. Shaleen highlighted the need for larger trials to validate these findings due to the small sample size. Nevertheless, this study opens new doors for treating bipolar disorder, offering a potential lifeline for patients who struggle with existing therapies. The research overall underscores the importance of innovation in mental health treatments and the promise of AI-TBS in reshaping how we approach bipolar disorder. So, continuing on the topic of psychology, I'm handing over the mic to Michelle to tell us more about recent research on the significant growth in toddlers' brains.
Thanks, Zena. A study recently done by the University of Oxford and the University of Bristol found that by 16 months old, toddlers use their left parietal cortex and both sides of their prefrontal cortex for inhibitory control abilities. This is the ability to prevent impulsive behavior, habits, or temptation, an important cognitive skill for toddlers to develop in their early years. The study used 103 toddlers and gave them a touchscreen task that tested their inhibitory control abilities, was being monitored through the child-friendly functional near-infrared spectroscopy to scan for active brain areas. The use of 103 16-month-old toddlers highlights 16 months old as a critical period for cognitive development. This study is beneficial as it gives insight into how the activity of brain areas become more involved throughout cognitive development. Now, swiftly moving on to mathematics, one of the biggest problems in math is a step closer to being solved. The Riemann hypothesis involves prime numbers and values greater than 1 that are only divisible by 1 in themselves, such as 2, 3, 5, 7, etc. 19th century German mathematician Bernhard Riemann proposed a way to solve the problem that prime numbers have no pattern and appear randomly with natural numbers that are divisible by other factors. He explains how prime numbers are distributed on the number line. Many theorems have been made based on this conjecture, and proving this conjecture has become a key point. The Riemann hypothesis does not predict where prime numbers are located, but poses that their appearance on the number line follows certain rules to support Gauss's prime number theorem. It states that the density of primes decreases and that primes are evenly distributed according to this density. There are no large areas in which there are no prime numbers at all or ones that are full of them. Riemann also linked the zeta function to prime numbers. He found that the zeta function has no zeros if the real part is greater than 1. The zeros of the zeta function are also known as negative values of the real part. But what really interested Riemann were the zeros of the zeta function in the critical strip between 0 to 1, in which all seem to lie in the straight line of x equals a half. Riemann hypothesized that all zeros of the zeta function within the critical strip have a real part of x equals a half. This is the center of understanding the distribution of prime numbers. If Riemann is correct, then the placement of prime numbers along the number line never deviates too much from the prime number set. Billions of zeta functions have been examined by mathematicians, and all zeta function zeros lie on x equals a half. Mathematicians are now looking for proof that there are no zeta function zeros that do not lie on the line to prove Riemann's hypothesis. They have also used a different approach by trying to show that there is a certain number n of zeros outside the straight line x equals a half to reduce n until n equals 0 at some point, therefore proving the Riemann hypothesis. Unfortunately, this path also turns out to be extremely difficult. Mathematicians have done the research and found that the worse the possible violations of the Riemann conjecture are, the more rare that they would occur. Their work has claimed to be able to apply to other mathematical theories and problems, which gives a new line of thought down in proving Riemann's hypothesis. Now I'm passing the mic over to Abby to tell us more about the properties of exoplanets.
Thanks, Michelle. We know what exoplanets look like, their mass, and even what they're made up of. But do we know what they smell like? A study from Johns Hopkins University used data from the James Webb Space Telescope to find out the smell of an exoplanet, known for its deadly weather. This Jupiter-sized gas giant has large amounts of hydrogen sulfide, a molecule that is known for giving off the smell of rotten eggs. The researchers predicted that the gas giant would contain hydrogen sulfide, as Jupiter also contains hydrogen sulfide, however it was never detected outside the solar system. This new research gives scientists information about how sulfur might influence the planet. Sulfur is an important element used in building more complex materials. Additionally, other elements like heavy metals, similar to those found on Jupiter, have been discovered, and the levels of oxygen, carbon dioxide, and carbon monoxide have been measured. In the future, they want to track more sulfur in more exoplanets and understand how sulfur influences planet formation near parent stars. Moving on, How do you think we protect frogs from deadly fungal diseases? Medicine? Isolation? Nope. Australian scientists have created brick refuges in greenhouses to help frogs survive infection. What are these brick refuges similar to? Saunas. This sauna treatment for frogs has been used successfully to fight off a deadly fungal disease that harms frogs all around the world. Recent results with endangered Australian green and golden bell frogs cleared infections of Batrachydrium dendrobatidis fungus in warmer greenhouse conditions. Many recovered frogs also became resistant to reinfection. However, this technique had failed with other frog species. This disease has caused the extinction of at least 90% of the species. Though this method may not be applicable to all amphibian species, it offers hope for the survival of the green and golden bell frogs.
That's all for today's episode. As always, you'll find the links to everything we discussed in the description.
Thanks for listening, and we'll catch you next time.